We're going to start our second to last unit today. Before we do that, just a little recap of where we've been. We started the year with no dimensions, so we just had a point. Points have no size, no shape. They are a infinitely small address or location in space. And then we put a bunch of points together to create some objects. And one of the first objects we created was the line segment. Line segment is just an infinite amount of points, but it also has a definite beginning and end. So it's measurable. It's one-dimensional. It's measurable. Because it's measurable, it has, oh, that's so big. It has length. There we go. And we can measure segments. We also measured some other things. But the basis of our next unit requires that we know how to measure length. And then from there, we moved into the two-dimensional world, where we looked at various types of polygons and more recently circles. Polygons made up of segments, other shapes like circles made up of no segments, and we could also have sort of a mix and match, segment and curve. And when we get into the two-dimensional world, we no longer have length, we now have area. We are going to move into area measurements for our next unit. So now we are no longer measuring things in inches or feet or centimeters. Now we're measuring things in square inches, square feet, square centimeters, and other units as well. Area in general, no, we don't need all that yet. Area in general is the number of unit squares inside a two-dimensional shape. And that's why we say square centimeters or square feet, because we're talking about how many squares of that unit can fit inside that space. Take square feet, for example. A lot of rooms in a house are measured in square feet. In fact, houses in general are measured in square feet. If you take a square that measures 1 foot by 1 foot, the amount of square footage inside of a house is the number of those 1 foot by 1 foot squares that would fill the floor space of the house. If you imagine everything removed from every room, so you just have a completely empty house, square footage is the number of 1 foot by 1 foot squares. When you have a smaller scale, you might be dealing with square inches. For example, if you're putting tile down into a certain room, so you're going to put down some tile in the bathroom. Those squares of tiles are measured in square inches quite often. When you start to have larger things like an empty field that you're going to divide up into lots, you might have a measurement of square yards. You may still use square feet, but you'll most likely use square yards because that keeps the numbers a little smaller. And you might even use acres. An acre is a measurement of so many square feet. Off the top of my head, I want to say it's 48,000 or so square feet, but that might not be entirely accurate. But an acre is a measurement of square feet. It's a lot of square feet. So that's what area is. How many unit squares can we fit inside a shape? Well, let's start looking at some areas. Start out with, I have a square. And what I have done is I have split this square into unit squares. Each of these squares are 1 unit by 1 unit, hence the name unit square. So this little tiny square here is 1 by 1, this is 1 by 1, and so on throughout the whole picture. And this is one way to find area. You take a polygon or take a shape and you split it into all these unit squares, and then you count the squares. And for nice perfect figures, that works just fine. In general, not so much. You'll see why that fails in a few minutes. A better way to find the area for this particular figure is to realize that because I have a square that measures 4 on each side, I'll have 4 squares that way and 4 squares that way. For a square, we say that this is the area. Let me write it this way. S is the length of one side. And because a square has equal sides, we are taking one side multiplied by itself, and we get S squared. Now a square is also a rectangle. I'll come back to that shortly. We also know that a square is a parallelogram. It's a special kind of parallelogram. And I'll come back to that shortly as well. Speaking of rectangles, here's our next figure. A rectangle. Obviously not drawn to the same scale as a square is. We'll assume these are all unit squares. I have 8 of them going across this way. I have 4 of them going down like this. 32 squares total. And the way we get that, of course, is to simply multiply this number by this number. And you may have been told a long time ago that the area of a rectangle is simply length times width. But now you know why it's length times width. You could also say it's base times height. You could think of this as a base. You could think of this as a height, because this does make a right angle. And you could use that as well. Just like here, you could use any of those. Because a square does have a length, it does have a width, it does have a base, it does have a height. They just all happen to be the same value. The rectangle, we have the 2 different values. Those are the 2 base shapes, especially this one, the square, that guide how area is calculated. Take a figure, split it up into a bunch of tiny unit squares, count all the squares. And that's where a problem arises. Because we don't always have a nice, perfectly square figure. Like this. Parallelogram. This unit square here can only go over so far. And this unit square here is outside. I can't draw another square here that's the exact same size because I would go outside the figure, just like I did here. And I can't squeeze another unit square here. So this is why unit squares run into some trouble. So we need a better way to do this. And with a parallelogram, we have a better way to do this. I'm going to draw vertical line like so, and I want to do it in a certain way. That's going to be a right angle. I'm going to start at this vertex, go straight down here, and when I do that, I create a triangle and a trapezoid. But I'm not going to calculate the 2 areas separately and add them up, even though that's what we could do. We could take a parallelogram and split it into a triangle and a trapezoid calculate them separately, add up their areas, and we have the whole parallelogram. But that's a lot of work. I'm going to cut this triangle out and glue it to this part over here. And when that happens, I end up with this figure. I know that this angle right here is 90 degrees because I drew this in such a way that I would get a 90-degree angle. Because it's a parallelogram, because this whole figure is a parallelogram, I know this is 90 as well. And I know this angle is 90. So when I bring it over here, I have 90 again. And this must be 90 to complete the quadrilateral. So I have taken a parallelogram and rearranged it so that it's now a rectangle. If I call this B for base, I know this is the exact same measurement. I will call this H for height, which is now this measurement right here. I still have B for base. I still have B for base. All I did was take this piece right here and move it over here. So I have not changed the overall length of the base. Because the area of a rectangle is base times height, or length times width, so is the area of the original parallelogram. It is base times height. Now there is a catch. The base must, absolutely must, be perpendicular to the height. This is not a height, ever. Never, ever. This is not a height. Never, ever. This could be a base if you have a height from here to here that's perpendicular to it. In other words, use blue. I could do this. I could do this. And then my base would be like so. As long as that's true, as long as that is true, you could use that base and that height. You must have a right angle, however. This height can slide left or right either direction. As long as it goes from this level down to this level at a right angle, it is a height. That is where the B and H come from in this formula, using a rectangle as a parallelogram. Here's our base, here's our height. We know they're a base and a height because this angle must be 90 degrees. Otherwise, it would not be a rectangle. In a general parallelogram, we get our right angle by going between the two bases at a 90-degree angle. One final formula for this first section. Triangle. And to do the area of a triangle, I'm going to use three figures. Start with the square on the left. Going to create a triangle like so. I will call this triangle A. I will call that triangle B. I'll do the same thing here. Whoa, let's try that again. There you go. Call this triangle C and D. And then I will do the same thing with this parallelogram. This will be triangle E, triangle F. Start with the square. I know that all four sides are equal. And I know that this side is shared between the two triangles. So this triangle is the same as that triangle. looking at triangle C and D. This side is equal to that side. This side is equal to that side. Shared side. We know triangle C and D are the same. With the parallelogram, opposite sides are equal, opposite sides are equal, shared side. We know that triangle E and F are the same. That's all we need to find the area of a triangle. In each of these figures, two triangles equals the base and the height. We could use base times height to find the total area. Base times height, total area, base, height, total area. So to find the area of one triangle, I merely divide both sides by 2. That's where the 1/2 comes from in 1/2 base times height. Area of a triangle is half the area of a parallelogram with the same base and height. To illustrate that, I'm going to make a copy of this parallelogram here. And then I will bring it down for a closer inspection. We'll say this is the base. Here's the height. Actually, I don't want to do that. I'm going to do it this way. Here's the triangle. Let me outline this triangle in blue. Here's the triangle we're taking a look at in blue. I know that this is the height of the parallelogram. I also know that I can move this height left or right and it's still the height of the parallelogram. Still the height of the parallelogram. Still the height of the parallelogram, and it's also the height of the triangle. When your triangle is obtuse, sometimes your height is outside the triangle. So what we do is we pretend that the base goes a little further, and now we have our right angle between base and height. But careful. This is not part of the base. It's a convenience to help us understand this is the level that the height comes down to. If this was made longer, the height would come down and hit that. This can't be a height because that is not a right angle. This cannot be a height because it is not a right angle. This is a height because it makes a right angle to the same level where the base is located. Even though the base only goes from here to here, if it were made longer, that's where the height would come down to. That is the height. It's the distance from the vertex straight down to the base. The height is also an altitude of the triangle. Every triangle has 3 altitudes. So theoretically, every triangle has 3 bases. Here's a base and a height. Here's a base. And a height. Here's a base. Different color. Here's a base. And a height. Every triangle has 3 sides, so every triangle has 3 bases. Every triangle has 3 altitudes, so every triangle has 3 heights. The trick is getting the correct base with the correct height. Base must be perpendicular to height, always. Always, always, always. But it also gives you three options. If I know what this base is, and I know what this height is, I can find the area of this triangle. Just like if I know what this base is and what this height is, I can find the area of the same triangle. And I should get the same answer. No matter which set of data I use, if I use the green or the black or the red, I should always get the same answer because they all go for the same triangle. Make sure you do your completion quiz for this section and email any questions that you may have.